So till now, we have been looking at hypothesis testing and estimation as examples of generic examples of estimation statistical inference problems. For hypothesis testing, what we introduced is a Bayesian formulation where we have a prior distribution before the experiment starts on the unknown. So for the binary case, we know that h0 occurs with some probability p, let's say, and h1 occurs with probability 1 minus p. And what we were able to do was that using a simple calculation, we were able to show that for uniform prior, when you don't have any reason to prefer h0 over h1 to begin with, that's roughly what you can think of as a uniform prior. For uniform prior, this optimal probability of error that you can attain is 1 minus half into 1 minus total variation distance between the distribution under h0 and the distribution under h1. Okay. So this test, the corresponding test was called a Bayes optimal test, and what you can see is that it is this simple form here. Okay, so the Bayes optimal test declares 0 when the probability under 0 at 0 is more than probability under 1, and it declares 1 when probability under 0 is less than probability under 1. Okay, this is an alternative form of the test that attained this performance. PE star uniformed, we wrote, was half into 1 minus total variation distance between W0 W1. Okay, they are attained by this test. Now you can take a log of both of these ratios, and so equivalently you can express this test as it will declare 0 if the log likelihood ratio exceeds 0, and it will declare 1 if the log likelihood ratio is less than or equal to 0. Okay, so in general, this form suggests the following form of tests, which are very popular in practice. These are called log likelihood ratio tests, thresholded log likelihood ratio tests. So here you will declare 0 if the log likelihood ratio of 0 versus 1 exceeds some threshold tau. Okay, this is some threshold tau, which is a feature of the test in the sense that you have to define it to use this test. And it will declare 1 if the log likelihood ratio of 0 by 1 is less than or equal to tau. Okay, so if you prefer W0 over W1 in this sense, then you declare 0, and if you don't prefer W0 over W1, then you declare 1. Okay, so this is an important class of test which is used in practice. Now, how did this test come about, or is there any theoretical guarantee for this test? That's what we will show now. In fact, this class of tests for different threshold are optimal for what is called the Neyman-Pearson formulation. Let me describe the formulation. Before we do that, let's see how well this test performs. So we will denote this test by G tau, where tau is the threshold. So under x0, when the true distribution, okay, so this is slightly confusing. Yeah, when the true unknown hypothesis is 0, this is binary hypothesis testing. Then under that, the distribution of observation is W0. So the probability of error under 0 is that firstly 0 occurs, and then you declare 1. So you declare 1. And for any such y where you declare 1, this will be an error. So this is one part of the probability of error. The second part of the probability of error was that in fact the true hypothesis was 1, but you ended up declaring 0. So all such y's with their probability measured under 1 is the second part of probability of error. We just abbreviate this px1 as p. So the probability of error is 1 minus p into W0 of this test declaring 1. So you measure this probability under W0 time plus p is the probability of 1, under W1 the probability that test declares 0. Okay, so this is your probability of error. In fact, these two probability of errors here are of different style. So this one where you declare 1 under 0 is typically called error given. This is the error given 0. This is typically called the type 1 error, and this is called the type 2 error. These are two different errors associated with a test. Okay, so one way to think of hypothesis testing problem is that it's a decision making problem, but the cost function is this pair W0 was comma W1. We have weighted this with this p to come up with a single cost function, but the actual cost function is a pair. So as tau increases, you can check as the threshold increases, a type 1 error increases, but the type 2 error decreases. So as threshold increases, you decrease the number of points included in 0. Okay, but you increase the number of points included in one. So you can verify that what happens is type 1 error increases, but type 2 error decreases. So what Neyman and Pearson did, they considered a slightly different formulation. They considered a slightly different criterion for optimality for a test. Till now, we were looking at average probability of error. The Bayesian formulation we looked at had average probability of error. But here is another way to use this pair to define a cost function. So we seek tests. We seek tests for which the error of type 1 is less than epsilon. Error of type 1 is less than epsilon. So this is the reasonable expectation from the test. No matter what, the error of type 1 must be less than epsilon. Under this constraint, we seek the best test. Okay, so what is the best test once we impose this constraint? We want to find a test that minimizes the error of type 2. So it minimizes the error of type 2 subject to the constraint that error of type 1 is less than or equal to epsilon. That's the optimal test. So we'll call this quantity beta epsilon w0 w1. Okay, so beta epsilon w0 w1. Now why beta? Typically in hypothesis testing, 1 minus epsilon is called alpha. It's sometimes called the power of the test. It's called the size of the test. This is the power of the test. Okay. So we are just calling it beta. It's just a convention. So beta of epsilon w0 w1 is the minimum probability of error of type 2. This is the probability of error of type 2. Given that the probability of error of type 1 is less than or equal to epsilon. That's what we are looking for. That's this beta epsilon w0 w1. Okay. So why does this formulation make sense? For many reasons. But here is a very simple heuristic reason. So think of an application where H0 is a normal operation and H1 is an alarming situation. For example, H0 can be absence of a disease and H1 can be presence of a disease. So here the error of type 1 says that it was actually the disease was not present, but you declared that the disease is present. So this is a false alarm. It's a less severe kind of error. So you don't want to declare false alarms. However, the error of type 2 is a missed detection. The disease was present, but you didn't find it. Okay, and this is a very severe error. And therefore, it makes sense to ask for a nominal guarantee of a small false alarm while minimizing the misdetection probability. Okay, that's what Neyman-Pearson formulation does. Alright, so let's evaluate our threshold test, the threshold test GT that we defined earlier, the threshold test on log likelihood ratio for this setting. So what is the probability of false alarm? It is given by this. So if you substitute for GTY as the log likelihood ratio test, so it will declare 1 if this log likelihood ratio is small. So probability of error of type 1, the false alarm probability, is probability under W0 of those y's for which log of W0 by W1 is less than or equal to tau. Similarly, probability of misdetection is W1 of y of those y's for which W0 by W1 log of that is greater than tau. By the way, we can so let's try to derive a bound for this probability of misdetection. So here is what we can do. We can express this W1 as W1 by W0 into W0. So this is sometimes called a measure change argument. The probability measure under which you wanted to measure things was W1, but you shifted it to W0. And there's a correction factor that you need W1 by W0 here. Okay. So how does it help you? Well, this condition here tells you that W0 by W1 is more than tau. For all, we are only summing over those y's. So over all these y's, actually, you can see that this ratio, which is just 2 to the power minus log of W0 by W1, okay, this ratio here is less than tau. You can see that. So this is greater than tau, so therefore minus of this is less than tau. Therefore, this probability is less than summation over y 2 to the power minus tau times W0 of y. So we made a measure change argument. We were first measuring the probability of this set under W1. We shifted it to a probability W0 at this cost of this additional factor 2 to the power minus t. In fact, this summation is over the same set. Okay, it's over the same set. However, if we remove this restriction, it will only increase the probability. So I can remove this restriction. And so this is not equality, it's only an upper bound. But what can you say about summation over y W0 of y? Well, that's 1. That's at most 1. That's exactly equal to 1, since W0 is a probability measure. It's a probability distribution, it's a PMF. And therefore, the upper bound that you get for probability of misdetection for this threshold test with threshold tau is just 2 to the power minus tau. Very simple. Okay. So for this threshold test, the probability of misdetection is no more than 2 to the power minus tau. So what have we shown? We have obtained a bound for beta epsilon. What we have shown is that suppose you can find a lambda that satisfies this property. So this is much like the source coding theorems that we were seeing earlier. This lambda, what it satisfies is that under W0, the probability of log likelihood ratio W0 by W1 exceeding tau is at least 1 minus epsilon. This will ensure that, this will ensure that the probability of error of type 1 is, so this is your probability of error of type 1. We want this to be less than epsilon. So 1 minus this, the complement of this event is where this is greater than tau, and we want that event to have probability greater than 1 minus epsilon. So that's the condition that we impose here. Suppose this condition holds, then the probability of misdetection is less than 2 to the power minus tau, and therefore beta epsilon, which is the smallest probability of type 2, given that a test satisfies this constraint, must be less than this. This is the smallest probability. I'm giving you one test which satisfies this probability of error guarantee. Therefore, the smallest can only be smaller. So we have shown this. This is, you can think about how the argument I just went through, how we have shown this. So what is our test again? The threshold test. But we have additionally assumed something about the distributions. We have assumed that this tau is chosen in a very specific way. We assume that this tau is a large probability. This is my large probability, lower bound on the log likelihood ratio. Log likelihood ratio. So this thing is called the log likelihood ratio. Its likelihood is this guy. This is the likelihood ratio, and this is the log of it. It's a log likelihood ratio, LLR sometimes. Okay, and so we have seen this very simple formulation here. Okay, so we have a handle over beta epsilon W0 W1. It's at most to the power minus tau. Okay. So now let's look at the case of IID. This is a general result. Let's look at the case of IID observations. Okay, so when IID observations are there, so we can find such an estimate. All we have to find is an estimate for this tau to get this upper bound. So if W0 and W1 are IID repetitions, as was in our coin toss examples, W0 will be this product distribution and W1 will be some other product distribution under Q. Maybe I should not use small q here. I've been using capital. Sorry. Yeah, I've been using capital P and Q. So P of this, P of this, and Q of this. Okay. So the ratio W0 by W1 is product, ratio of these two products. And there's a log. So the log makes product sum. So again, make it capital P and Q. So what is a good estimate for this guy? Well, we can use Chebyshev's inequality. A good estimate for this guy is expected value of this quantity plus some square root n times variance of this quantity. So n times expected value plus variance. This is just Chebyshev's inequality. Since these guys are independent, okay, this variance is just sum of variances. That's some important property we saw earlier. This is what we have been doing right through, right? We have been finding estimates of log of 1 by, remember this part? We've been finding estimates of log of 1 by pxn id random variables. It's a similar calculation. That's how we found entropy. So what this calculation suggests is there is something special about this expectation. Just like we discovered entropy as expectation of log of 1 by p, now this log of the expectation of log of likelihood ratio. By the way, this expectation is under p, and this is very important because we were measuring this probability under W0 and W0 was under in the numerator here. Okay, so this expectation is under P. So this quantity basically gives you an upper bound on beta epsilon W0 W1 because we have an estimate for this large probability upper bound on log likelihood ratio. So this, for IID case, the upper bound that we have is 2 to the power minus n. The expected value under W0 of log of W0 y Let me make some space for myself. 1 second. So expected value under W0 of log of W0 y. This y has distribution W0 y, W1 y, and n times this. So this probability of error goes to 0 very fast in n. It's exponential in n, and the exponent is this guy. And this guy has a name. This guy is called the Kullback-Leibler divergence. And the fact that this probability of error can go to 0 very fast has a lot of interest, has received a lot of interest, and this is what we'll discuss in the next lecture.